Hello everyone, my name is Franco Pucci and I'm the Technical Consultant for the STS Association. I've been involved in the prepayment industry for over 25 years. Welcome to the STS training video series where we will explore all aspects of STS and the STS standard. I hope you find these videos helpful. In this video, we will deal with sections 6.5 and 7.3 of the IEC 62055-41 specification, and that deals with algorithms. First of all, the decoder key generation algorithms, that's under section 6.5.3. Let's look at the PAN block construction. The PAN block construction is as shown. You have 16 bits essentially. The first 3 bits are 0 to 9, and they are the issue identification numbers. The next few bits, all the Ds, are also 0 to 9, and they are the DRN number. Now you will notice that bits 11 and 12 could either be an IIN or a DRN number. That depends on whether you have a 11-digit or 13-digit meter number, or in other words, a 2-digit or 4-digit manufacturer code. For a DCTK coded meter, that's a meter that's coded with a common key, the DRN is all set to 0. So the reason for that is because these meters are all coded with exactly the same meter key. Therefore, the DRN is actually meaningless. For an 11-digit DRN, use bits 11 to 15 for the IIN, and for a 13-digit DRN, use bits 13 to 15 for IIN and bits 11 and 12 as part of the decoder reference number. The control block construction, which is can be found in 6.5.3.2, that also has 16 bits, and there we have a key type digit, the C, bit 15, value 0 to 3. You have a supply group code, which is made up of 6 digits, 0 to 9. You have a tariff index, 2 digits, 0 to 99 in fact, and you have a key revision number, the sixth bit, which is 0 to 9. The F digits are always set to 0 in the control block construction. So we can see that the decoder key depends on IIN, which is either 600727 for 2-digit manufacturer codes, or all zeros for 4-digit manufacturer code meters. The DRN is unique for each meter. The supply group code is unique for the vending key. Now you can have the same vending key, the same supply group code with different vending keys if the key revision number changes. Tariff index, which is unique for the meter or group of meters. The key revision number, which is unique for a vending key revision. Key type, that would be a unique, default, or common key. Changing any of these parameters will then change the meter key. Now let's look at the DKGAs themselves. DKGA01 is very limited use. It was used for a small group of prepayment meters that conform to certain DRN ranges and certain supply group code values. And if you want a list of these, you can look at the IEC 62055-41 document. You'll find them in there. DKGA01 should not be used for new designs. It was very early. And it uses the data encryption standard, which is now no longer specified and in fact deprecated. DKGA02, which is the current meter base, has all DKGA02, or 99% of it at least. It's used for most meters installed in the field. It should not be used for new designs because it does not have support for multiple base states. You can of course still support it. If a customer wants, you can still support this for a while, but remember, by 2024, once the TID rollover is completed, DKGA02 becomes obsolete. DKGA03, which is also specified in the IEC document, is deprecated. Do not use that. And then, of course, there's DKGA04. That should be used for all new designs. Remember, with DKG4 you can still use EA07, which is the STA algorithm, and you can also use EA11, which is the MISTY1 algorithm. It does support multiple base states, and it is STS edition 2 compliant. It uses a key derivation function based on HMAC SHA-256 algorithms. It can be used to generate 64-bit or 128-bit keys. These algorithms are only implemented in the security module, so the meter doesn't have to be concerned about which algorithm was used. It only cares about a decoder key. However, the security module attached to the point of sale must support these algorithms. Okay, if we have a look at the encryption algorithms now, these are the bits that are actually in the meter, then we will see that the encryption algorithm EA07, which is the STA algorithm, and you can find it in 6.5.4, is used for most payment meters installed in the field. If we go through the picture on the right, there's a 64-bit key block, there's a 64-bit data block, and some arithmetic operations happen to it. You do a ones complement, you rotate the key 12 bits, then you do a 16 times substitution, permutation, and key rotation on these, and then you'll end up with an encrypted data block. We obviously won't go through the details of this, but if you wish, you can have a look at it in the specification. There is an example, in fact, in the -41 specification. This algorithm may be used for new designs. It uses a 64-bit meter key. It's based on a DES algorithm. The HSM uses this algorithm to encrypt tokens. The meter uses this algorithm to decrypt tokens. It is only implemented in the security module, so you don't need to implement this other than the security module. In fact, it's also implemented in the meter. My apologies. The permutation and substitution done using published tables. Now, there are tables contained in the 62055-41 document. Those are sample tables, and all the examples in the document are based on the sample tables. And there are real tables which you can get from the STS Association. Okay, if we look at the decryption algorithm, then you will see that's also EA07. You'll see that used for most payment meters installed in the field. It may be used on new designs. The flow of data is almost the same as the encryption portion of it. You can follow that if you wish. It uses a 64-bit meter key based on the DES algorithm, and the meter uses this algorithm to decrypt tokens. This one is only implemented in the meter. What I said earlier in the previous slide is the encryption, in fact, is only implemented in the security module, and the decryption is implemented in the meter. The permutation and substitution tables you can refer to IEC 62055-41 to get those tables, and also to look at the process for rotation, substitution, and permutation. It gives you a pretty good example of how to do this with the worked example. The encryption algorithm EA09, which you can find in 6.5.5, is deprecated. Encryption algorithm EA11, which is the MISTY algorithm, that one uses a 128-bit key block, a 64-bit data block. The MISTY1 encryption algorithm, which results in an encrypted data block. There is also an example of this in 62055-41. This may be used for new designs. It is a much higher strength than the EA07 because it uses a 128-bit meter key. It's based on the MISTY1 algorithm, which is now an international standard. In fact, security modules use this algorithm to encrypt, and the document or the specification for MISTY1 is ISO 18033-3 if you wish to download that document. On the decryption side, EA11, it looks exactly the same. You have a key block, a data block, and you use the MISTY1 decrypt function, and you land up with a decrypted data block. Again, may be used for new designs. It pretty much as before uses a 128-bit meter key based on the MISTY 1, and the meter uses this algorithm to decrypt tokens. And also you can see ISO 18033 for MISTY 1. It's a symmetrical code, so symmetrical cipher, so you can actually use the same code in both the secure module and the meter. This brings us to the end of this part of the video series. I hope you found this video helpful, and I hope you will join us for the rest of the series. Goodbye and see you again soon.